All right, let's get started on Chapter 2. The idea of systems of linear equations shouldn't be new to any of you. You should have seen these before. So some of the stuff we're going to be doing will be very familiar. The new thing is we're going to introduce a new notation that some of you may not have been, and it's introducing a matrix, a way of dealing with a system, but we only actually work with the coefficients, and we don't have to keep writing x's and y's and z's and equal signs every time. The reason we care about systems is each equation captures information, and together the information can narrow down the solutions for all of these. The way to interpret systems like this, we can do it in two ways. One, this is the intersection. The solutions are intersections of planes, if we're talking up here, or lines here. If we have four variables or more, it's hyperplanes. But there's another way to interpret these. So we could rewrite. I'm going to rewrite this setup here. I could rewrite this as x times 0, 2, and a minus 1. Those are the coefficients of x, plus y times a negative 3, 2, and a minus 1. Adobe doesn't like curves. Plus z times 1, 2, and a minus 1. And we end up with 0, 5, and a minus 1. Okay, so these are equivalent. Like this set and this set, these equations are equivalent. But this we interpret differently. This is how much of each of these vectors. Okay, this is more like the food analogy. Like how much of each of these foods, if each of these is nutritional facts per serving, how many servings of each of those do I take to get this one? So there's a vector. This is the vector interpretation. This is the planes and lines interpretation, okay? And we're going to be going back and forth throughout this chapter and throughout this course. And we're going to end up doing this a lot more than this. We're going to leave the planes and lines a little bit. So we'll end up using vectors more. Okay. So what do we mean by a linear equation? It's an equation while all your variables are to the first power and you have coefficients and they're added together. I'm added or subtracted, you're not multiplying or anything. Okay, equals a constant. The a's and the b's are real numbers. These come up a lot, and if the application isn't exactly linear, often they can be approximated with linear equations. And sometimes we have hundreds or thousands of variables. Luckily, we have computers to help us out with that. But they can't solve everything. In fact, they just give rise to other problems we have to work on. We'll talk about that later. So these are some examples of linear equations. So this looks crazy, but really that's just a real number multiplied by x to the 1 power. Sine of 5 is just a real number. So 3 squared is just a real number. Here, these are non-examples. We've got a square there. We've got a square root, which is to the 1/2 power there. We've got sine of x to the 1. So this is a nonlinear function. So we've also got two variables that are multiplied together. So these are all problems down here. If we have more than one equation, we call it a system. They're connected, like the variables are the same, so that's what they're connected with. And when we write them together, it means that we're looking for values x1, x2, and x3 that we can plug into both equations, or 3 or however many equations, and they satisfy all of the equations, so they make each of them true. That's what a solution is. We call two systems equivalent if they have the same solution set. I should have warned you up front, there's lots of new vocab in the beginning of chapter 2 here, so lots. So this is a solution. This is an equivalent set to this because the solution set is the same. We're going to talk about how to connect those. In two variables, they're easy to interpret. We already talked about that you can interpret them as lines. So if you have two equations, they intersect at one point, you get one example. Awesome. One intersection, you get one solution. If they're parallel, then they don't intersect, and so there's no solution. If they are the same equation, then you get infinite solutions. And it turns out that these are the only three options when you are looking at a linear system, not just lines, but including planes and hyperplanes. If you have a system, then you either have one solution, no solutions, or infinitely many solutions. There are different ways to end up with those when you're dealing with planes. All three could be parallel, but it doesn't matter. As long as two are parallel, you're not going to get an equation. You're not going to get a solution, but here's 1 point. Here's infinitely many points on a line. You could have infinitely many points on a plane, but those are the only options. If there's at least one solution, we call it consistent. And if there's no solution, it's inconsistent. Consistent can mean one solution or infinite. It doesn't matter. As long as it's got a solution, it's called consistent. So these are often the first things we're looking for when we have a system. We want to know, is there a solution, and is that solution unique? Is there only one? Does at least one solution exist? That's the consistent question. If a solution exists, is there only one solution? So is there just the one, or is there infinitely many? There's no option for two or three or finitely many. If there's more than one, there's infinitely many. And the reason is you can't get two lines to intersect at only 2 points, or a line and a plane and two planes to intersect at only 2 points. If they intersect at one or infinitely many, depending if your lines are planes. Okay. So to save us some time, we're going to avoid writing down a lot of the x's, or the xyz's, or the x1s, x2, x3s, x4s. And we're going to just use this notation. This is called matrix notation. So we have a big bracket and on both sides, and we just write down the coefficients. So it was a coefficient of 1, then a coefficient of 3, then 2, then 3. And then 0. We didn't have something here, so we've got to put a 0 there. So those are the matrix coefficients. This is a matrix of coefficients. We often just say the coefficient matrix. We can also include these if we want, and if we are including them, then we draw a line where the equal signs are, so we can signify. And so we haven't lost any information with this. We can go and write that down too. So we haven't lost any information, but it is cleaner in some ways. And we will go back and forth, especially we'll work with this to get solutions, and then we'll go back and write the solutions in the terms of x1, x2, x3, and x4. Matrices have different sizes. This is called the 3x4 matrix. These are rows, and these are columns. And we always use the rows first when we talk about the sizes. So it's a 3x4. You could have a 2x1. That's a 2x1. So you can have all sorts of different sizes. We don't really use 1x1s. 1x1s are just a real number, so then it's no use talking about matrices. So an m rows and n columns in general, we just call it an m by n matrix. Okay. So we can modify an augmented matrix without changing the solution of the corresponding system. Okay, that sounds like a lot, but you guys are actually, you guys already know how to do this. You just haven't done it in terms of matrices, perhaps, but the way that you solve systems of equations with elimination are going to be the tools that we use. So if I have 2x plus 3y equals 5, and x minus y equals 0, then we can start doing tools. You guys know about elimination, so I could multiply this by a negative 2 and then add, and if I did that I would have 2x plus 3y equals 5, and then that second one would be a negative 2x minus 2y equals 0, and then you add those together. I get a new equation. I get 0, I get y equals 5. I'm sorry, yeah, 1y equals 5. Now a lot of you would replace y equals 5, you'd eliminate this one, or you'd eliminate this one of those, and so you have y equals 5 and x minus y equals 0, and and then you go from there. Now you can do substitution, or you can do another elimination and add these together, and you get x equals 5 also if you add those together. You don't even have to multiply by anything, you get it right. Or you already know y equals 5, so you can plug 5 in there, so you get it x minus 5 has to equal 0, and you can solve. Okay, those operations, those things you're already comfortable with doing here, comfortable with I hope, they are the basis for row operations. So we can replace one row by the sum of itself and multiple of another row. Here, let's start with these. These are the easier ones. Okay, you can interchange two rows. It doesn't matter if we go back to the system and I rewrite x minus y equals 0 and 2x plus 3y equals 5. It doesn't matter if I write it. I don't know why it does not like curves. Okay. It doesn't matter if I had written it this way with the 2x plus 3y up on top or the x minus 1 on top. It doesn't matter. Still the same system. So, and that corresponds to interchanging rows. So we can write 1, a minus 1, 0, 2, 3, 5 as an augmented matrix. Or from this one, shouldn't have crossed that out, 2, 3, 5, and 1, a minus 1, 0. These are the row operation of swapping those that keeps them row equivalent. Okay, it won't change the solution. So we can multiply all entries in a row by a non-zero number. We did that over here. We multiplied this row by a negative 2, so we could add. So it doesn't change the equation. If you have an equation of line and you multiply it by a constant, it doesn't change it, as long as the constant isn't 0. And we can replace one row by the sum of itself and a multiple of another row. So we did take one row, multiplied it by a minus 2, then we added it to another row, we added it to that first row, and we got a new equation. And this says we can take this new equation and we can replace it with one of these rows. So so the operation 2, 3, 5, 1, a minus 1, 0, if we had this, I can take, this is row 1, this is row 2. I'm going to take this first row and replace it with row 1 plus a negative 2, row 2. So this is row 2. So I'm going to multiply that second row by row 2 by a negative 2 and then add. And so then I'd get 0, then a minus 2. I'm multiplying this row by a minus 2, and I'm doing some of these in my head, but minus 2 times this minus 1 is 2, and then I add that to 3 to get 5. And then the 0 times a minus 2 plus 5 is just 5. Oops, did I make that mistake? I think I made a mistake before. Well, that wasn't very good. I missed a made an operation. Oh yeah, so that should have been a positive. No wonder it didn't come out the way I thought. Okay. So we get 5, 5. So if I had done the other one correctly, Oh, yay. 2x plus 3y equals 5. 1x minus 1y equals 0. This is the same as that, right? We multiplied this by a minus 2. That becomes a positive 2. Added together, I get 0. I get 5y equals 5. And so now I have a new equation, and I'm going to get rid of this. I'm going to get rid of the first and keep the second. So I'm going to replace that. So we could do that if we just did equations. We can do that just with matrices. Okay, so those are our three operations. Okay, we can replace one row by the sum of itself and a multiple of another row. We can interchange two rows. We can multiply all entries in a row by a non-zero number. And the key is that those do not change the solution to the system. Okay, these are steps we can do to find solutions to the system. Two matrices that can be joined by a sequence of elementary row operations are called row equivalent. Okay, so we're going to try to find row equivalent matrices that are really easy to work with or very easy to solve. And this is the claim I just made. These row operations do not change the solution set of the system. So here we have a system. Not too bad. Is it consistent? What does consistent mean? Consistent means it has at least one solution. Well, this seems like the nice place to start. So what does x3 equal? x3 equals 2, because I can divide both sides by 2, and I get x3 equals 2. And now I know x3, I can plug 2 in for x3 here, and that's what this equation is here. So the x2 minus 2 times the 2 equals 3. You can solve for x2, you get 7. And now we know what x3 and x2 are. You can plug them back into here. So this is 7, this is 2. Then you can solve for x1, and you get a negative 29 divided by 2. So, so that's x1. So the solution is the x1 equals that, x2 equals that, x3 equals that, or in vector notation, we write it this way. So that's the coordinate. If that's the coordinate that satisfies all three of those equations. Or in terms of vectors, if you're finding combinations of vectors, then you take this much of the first vector, this much of the second vector, and this much of the third vector to equal a negative, the vector a negative 4, 3, 4. Okay. So this is called back substitution. Once you have it solved, so we're in this triangular form, then it's really easy to solve, and you can do back substitution. You solve for the simple one. You only have one unknown. You place that up here, then you only have one unknown there, and then you replace them both up there. You only have one unknown. That's called back substitution. So one strategy is to do row operations with a matrix to get it like this, and then do back substitution. Okay. So we need a little bit more language to know how to get it into the right form. That helps us a lot. So that's what the first part of this one is. So a leading entry in a matrix is the first, it's the first non-zero, first meaning from the left, first non-zero entry. So this is a leading entry. This is a leading entry. There are no leading entries in here. Okay. So every row we're looking for the leading entry in each row. Leading entries can help us define certain forms, and these are going to be the really nice forms that help us solve equations. So a matrix is said to be in row echelon form if both of the following conditions hold. All rows entirely of zeros are at the bottom, and each leading entry of a row is in a column to the right of the leading entry of the rows above it. Meaning we're going to have this kind of thing. Oops, wrote down too many there. So we want this effect. So the reason this is called echelon, it comes from the same word, a lot of you that speak Spanish. Escalera means stairs or ladders. So, or escalator, it's the same word that we get escalator from. It basically means stair steps, right? And you can see the stair step, the stepping pattern here. So once we get a leading entry, we don't want any more leading entries below that. And in the next row, the leading entry has to be to the right of anything above it. So that's what this is saying. And reduced row echelon form, it goes a little bit further. It's in row echelon form, but all the leading entries are 1. So up here, we'd have to change this to 1 and change this to 1 using row operations. That means these might change. And each leading 1 is the only non-zero entry in its column. So this is one. Here's one that we're not in reduced row echelon form. We've got to change these to 0 somehow through row operations. So I think we have some examples. Yep. So here, this is in echelon form. If we look at the zeros, we get the stair step effect for the following the leading entries. This is not in echelon form because we have this. This is a leading entry and this is a leading entry, and you want to have any leading entries in rows above it have to be to the left, and that's not the case here. So neither of these are in row reduced echelon form, because this would have to be a 1. This would have to be 1. Those are our 2 leading entries, and then this would also have to be a 0. Okay. Which of the following matrices are in echelon form and which are in row reduced echelon form? So this is in neither, because the zeros all have to be in the bottom. This is in row reduced echelon form. If I look at any leading entry, all of the leading entries in the rows above it are to the left. So I have the 3 leading entries here. None of them are stacked. And all the leading entries are 1, and all of the other entries, in the columns where I have leading entries, all of the other values are 0. So that's row reduced echelon form. You'll get really comfortable with these because we're going to use row reduced echelon form a lot throughout this semester. I actually think that's as far as we need to go, but we should do an example. Yeah, let's do this example. So find the pivot positions and columns of the matrix. So this walks through using the entries, and there is a strategy. In fact, the strategy is down one more page right here. So we're going to start with the upper left. We're going to start up here, and then we're going to use that leading entry to get the ones below it 0. And then we're going to go to where the leading entry in the next one, and in the next row, and then you get the one below it 0, and then we're going to get the leading entry in the next column. If it's our last one, we use that leading entry, and then we use it to get the zeros above it, and then we come back to this one and get the 0 above that, if possible. So if we have a 3 by 3 and we only have 3 leading entries, or if we have 3 leading entries in 3 rows, then hopefully we can get them all to be zeros. So I'll let you come back to this and carefully look at these, because the strategy is you're going to use the ones to make the other things zeros by adding, and when you don't, where you want a 1 that isn't a 1, you're going to use multiplication. So what do we do here? We're going to start with this 3, and let's try to get this to be 0. So if I multiply this top row by a -2 and add, then I can get that to be 0. So that's what That was the first step here. So you get, oops, I said -2, I meant 2. So this is going to become a 6, and this will become a 4, and this will become a 2, and this will become a 0. And then when I add the 6 and the 6, I get this 0, and the 4 and the -4, I get that 0, and the 2 and the 3, I get a 5, and the 0 and the 1, I get a 1. And then we're going to, similarly, we're going to use this 3 to get rid of that 9. So we're going to multiply that top row by a -3, and then add it to that bottom row. So, and if we do that, because we'd have a -3 times 3 would be a -9. We add, we get 9. We get 0. A -3 times 2 would be -6. So add to 6, we get 0. -3 times 1 is a -3. Add to a -2, we get a -5. Yep. And whatever times 0 is 0, plus a -1 is a -1. So that's how we got that row. And now let's get this. We can use this second row. Here's our leading entry, 5. Let's add it to this bottom row to make that 0. And that 1 adding to the -1, it makes that 0. So we end up with a row of zeros. We need that at the bottom. It's already at the bottom. Awesome. And then we want our leading entries to be 1. So we'll multiply by 1/5. So now this is 1. And let's multiply this row by a -1 and add it to this row to get this to be 0. Because once we have a leading entry in a row, we want to make everything else, all the other terms 0. All the other entries 0 in that column. And so when we do that, this -1/5 would add up to that 0, and we get a -1/5. And now we just have one more thing to do. We need to turn that 3 into a 1. So we can multiply by 1/3, that whole row by 1/3, and we get 1. So now we have our 2 leading entries. They're 1. Everything else in those columns with the leading entries is 0. The leading entries are called pivots. And once we get it to row reduced echelon form or reduced echelon or row echelon form, those leading entries are called pivots. These are pivot positions, and columns or rows with pivots are called pivot rows and pivot columns. And yeah, if we only care about the pivots, and sometimes we do, then we only have to get it into echelon form. We don't have to get into reduced row echelon form. Okay, I think that's enough. You can look at this, and the other teachers already walked through this whole thing about how to do the steps. Using the first entry here. If that's not a 0, if it's a 0, then you can swap out a row where it is a you can swap 2 rows, so you can make it a non-zero, unless the first column is all 0. But use the 3 to get and that's what they did here, right? They swapped these to make that one a non-zero, and then they're going to use that to get that 3 0 by multiplying by -1, and then this is and now everything below that is 0, so you move to the next row, first non-zero, then use that to get the ones below it, etc. So you can pause it and look carefully at the steps that they do. We'll be working hard on this over the next couple weeks. We'll get this system down pretty easily. Okay, thanks everybody.